Hi, today I'm going to start to talk about the center of gravity, and later on I will start to talk about the centroid, or center of area, center of volume, or center of light. Um, to start to talk about the center of gravity, first of all, let's consider that um, when we want to talk about the gravity, most of the time we show the gravity as a weight. We say the weight of the object or body is that number. But in reality is that if you have an object like that, that object is gonna every every particle in that object is gonna have a weight. So it's gonna be have weight all the objects there. So weight would be applied on all the objects on that um, uh, any body we have. If you remember that what we have before for the distributed load, it was like that. If you have a distributed load, assume we have a being like that. We have a distributed load, any distributed load on that. We know that there's a resultant force for that distributed load. That will say that, okay, well, we have the resultant force applying somewhere. So it was a resultant force. And then we wanted to find the location of that resultant force. It's similar as the weight we have. So the weight is applied at every particle of the object, and the resultant force of all those mm, vertical forces, or the forces applied by gravity, is going to be the weight. And then we have the weight of object, and then we have the point that that force is going to be applied, and we will call that center of gravity, the total weight applied on the object. It means that if we add all the small weights that add all the forces applied at the single particles, add them together, is going to be the total weight of the object, and then the position that resultant weight is going to be applied is going to be the center of gravity. Right? We'll look at how we can actually uh, find that. First of all, let's start with the simple example in that case. So assume I have a rod, and assume there's a rod like that, and so there's it's a x direction, and that's the y direction, and I want to find the center of gravity of that rod. Now, in most cases that we know that is the center of gravity for that rod, assume is going to be located somewhere that we don't know, uh, with the distance of the uh, let's say, assume it's the center of the gravity for that rod, and this is going to be located as x bar. So it's where it's going to be located. And then assume we will have an element. We're going to just assume we have a small element somewhere on that rod, like that. And then it has the the center of gravity. That small element has its own center of gravity and its own weight. So assume I have a small element that it has the weight of dw, and its center of gravity is located at that. So its center of gravity has so it's the center of gravity of that small element, and has the dw. Now if I go ahead and put that force, put the gravity on them. So assume here I have the W apply here, and then here I have that D W, the small weight of the W, apply here. Apply there. Now to find the center of gravity, one way I can say, so let's write the moment about point O. The moment that weight, the total weight created about point O. So the moment about point O that the total weight created is going to be the weight times the distance x4. Now assume if I divide and then split the total rod, the rod into the very small element, a small element, and then I want to see how all those small elements create a moment about that point O. What I would have is that if this is a small element, I will go ahead and call that small element as um, Wi. So I would have that said, I would say the moment all those small elements is going to be, so add them all together, every small w, and the distance it has to point O. And then I know that so these two should be equal to the moment created by all the small elements. If I divide the rod into the small pieces and then add the moment every piece created about point O, it should be equal that the total weight created about point O. So if I go ahead and say, okay, these two should be the same, therefore what I would have is these two should be equal. In other words, the moment created by the total weight should be equal to the sum of the moment created by all the small elements in that case. And if I go ahead and make it into integration format, that would say that, or let's first, this is the one I want to find out, so that's the x part. So if I rearrange that equation, this is what I would get. So it's going to be sigma wi, the weight of that the weight of that particle. So the weight of that particle is going to be basically the weight of that is the dw, and the distance is going to be, and then it's going to be the total weight. And if I put them in the integration format, it's going to be and then the total weight is just add all the small weights. If I add all the small weight together, that's what I would get. I was just to make it probably easier to do. That's why I go ahead and say let me, so let's get rid of that. So, and it's probably easier to show it that way. So we'll go ahead and do all dw, add them together. So that's what I have. So it's probably easier that way. So if I go ahead and say that moment, the moment created by the total weight is the moment created by adding all the created by adding the moment created by all the small elements together, and then that's how we can calculate the center of gravity for that object. The same way, if we have the 2D object, is where the same thing. If you have the 2D object, in that case, the same as the x is going to be the center of gravity in the x direction, and for the y is the center of gravity for the element in the y direction. And the same way we can have it for the z as well, for the z direction as well, if we have the 3D option. And this is how we will do that for the for the center of gravity. Now, the next thing is I want to go ahead and talk about is the center of gravity and what is the center of area or center of the volume or center of the line. One point is that if before I go ahead and start talking about it, is that if we have an object, uh, if we have the object with the constant density, if the rho is constant, in other words, if we have the rho, the density of the particle we have, the principal object we have is constant, then center of area or the centroid, center of area, center of gravity, center of center of area, center of volume, center of line would be the same as the center of the gravity. So in other words, the centroid would be the same, is the same as center of gravity. This is one point we want to know that before moving here. So if we have an object that has a constant density, in that case, the centroid of that object is the same as the centroid of the gravity. So, but knowing that, the next thing I want to start to talk about it is we go ahead and start talking about the centroid, to see how the centroid, how we work with the centroid. So, the centroid. And I will start to talk about the centroid of area first. So the centroid can be, is the centroid, it can, most of the time we hear it as centroid, but it can refer to the centroid of area or centroid of the volume or centroid of the line. Well, start center of area is probably easier to start with, and then I'll go ahead with the center of the line. So one thing is that assume I'm gonna have an 2D object, a surface, in other words. So I assume I have a surface like that, and then there's a surface like that. That's gonna be our x and y axis, so it's gonna be x, y axis. So it's gonna be x, y axis, and I want to find the centroid of that, and I know that centroid of that is somewhere sitting here, and it has a value of x bar and y bar, and the centroid would be calculated similar to the way that we calculated to the center of the gravity. If you remember the center of gravity, what we did is we balanced the moment created by the resultant weight and the moment created by the small element in the object. If you balance them, it will say that the moment created by the resultant weight should be exactly the same as the moment created by each particle in that object, and balance them, that you will have the location that resultant weight is going to apply. The same way we will do that here, but this time with the area. So here we will go ahead and say that the centroid of that area, if we balance the moment created by area rather than the moment created by the weight. So look at here, this one is the centroid of the element, center in the x direction, so it's the distance, and this is the area, and we will say that this is the moment created by area, because area is times by distance, similar to the force. So we have the force times by distance, so it's the moment of force, so it's the moment of area, and similar to what we had there when we says we will find the centroid gravity, the same way we will find the centroid of the area or center of the volume. The same here, if in the y direction also go ahead and balance the moment of area, this is what we get. So we will get dA over dA. Now how we get, because this one we need to have the what to say, we need to have the center of the centroid of the element and the area of the element, and how we are going to get that. So let me redraw my 2D object. There are two ways of doing that. So one, so if this is, let me draw that. So it's a, assume this is my 2D object again. This is surface half, and one more time I'll draw that here. So assume the same object, we have it in the, it's going to be the x, y, and the y, and the same here is the x direction and then the y direction. We have two choices to do that. Look at here, we have to find the dA and we have to find the centroid of that element. So we have to find the element and the centroid of that element. There are two ways we can do that. If we can find the element is going to be vertically, or we can find the element go horizontally and use that element to find both of them. Remember, we use either this one or this one. We are not going to use both of these conditions that I'm going to talk about. We either choose element vertically and we do all the calculation, or we choose the element horizontal, we do all the calculation. So the first time, assume I will choose the element vertically. So assume this is the element I'm going to choose and work with. So if this is my element here, it has the width of dx, and then also has the height of y. It's going to be y. And then it has a centroid here, sitting here, and that centroid is has the x and y dimension. I need to find also those dimensions. So if I go ahead and look at the centroid dimension for what I have, again here, that distance so that distance is x, and this distance is half of y. So this is the location of the centroid of that element. So you define an element and define the location of centroid of that element. So the two things, define an element and define the centroid of that element. Now here, assume this is going to be the y is equal fx. So it's the same thing here. So y is equal fx. Same here, y is equal fx. Now if I have here, now I have to go ahead and for that element find dA and the location of the centroid. So the dA is gonna be y, the area of that element, dA is the area of that element, is going to be y dx. Now look at how I have dx here. Because I do have dx here, everything I'm writing should be as a function of x. So I have to get rid of that y and replace it by x. So I know that the y is function of x, so I'm going to just replace it with fx dx. And also I have the centroid of the element in the x direction is just x, and I have the centroid of element in the y direction is half of y. Again, this is in the y, so I have to get rid of that, so it's going to be half of fx. So I'm going to write it as a function of fx here. And then when I do have these things, and look at here, everything is going to be function of x because I do have the x and everything else is a function of x. I'm going to just replace it in these two equations and calculate the centroid. The other choice I have, so I can calculate both x bar and y bar with this element. I might choose to go ahead and choose the horizontal element rather than the vertical element. So assume I'll go ahead and choose the horizontal element like that. So this time this length is going to be dy, this length is going to be x, and then this is the centroid. Again, the centroid of the element, we want to find the dimension of centroid of element, so we know that the so this distance is going to be the centroid of the element in the x direction is going to be half of x, and the distance of the centroid of element in the y direction is just going to be simply y. It's the y. The same as what we did before. Here also I have to go ahead and find dA and this the location of centroid for this horizontal element this time. So this time dA is going to be x dy, and because I have dy, so I have to write everything as function of y. So therefore I have to go ahead and here find this equation and rewrite that equation as a x should be as a function of y. So rewrite it in a way that I get x as a function of y, and then I come here and then I would replace x with a function of y, and then I have dy. Then I have the distance, this center of the element in the x direction, which is going to be half of x, and then because we have everything in dy in this condition, I have to get rid of that x, going to be half of that fy that we calculated. And then the same for the distance of the or the centroid of the element in the y direction is just simply going to be y. And this time we can use these three values in this x and y equation here to calculate the x bar or y bar or the centroid. So we either use the vertical element or horizontal. So we are not going to use both of them at the same time. So either we choose to go with this one vertical, or we choose to go with this one vertical. If we choose to go with the vertical, everything is going to be function of x. Or if we choose to go in horizontal one, it's dy, so everything should be written as a function of y. In most cases, it's easier to go with this vertical one because everything is going to be function of x, and in most cases it's going to be easier to do that. Sometimes it might not, but it depends on the case, but in most cases it is. So this is how we will do the calculation for the centroid of the area. Now let's go ahead and see how we can calculate the centroid of line. So it's a 2D centroid, and let's look at the how to do the 1D centroid. So centroid of line. So again, assume I have uh, assume I have a line like that. I want to find the centroid of that line. I want to find the centroid of that line. Remember that, especially when we are talking about the line or linear object, the centroid might not be on the object. Always remember the ring. When you have the ring, the centroid of the ring is going to be off at the center of that ring. So it's very probable that the centroid of the object is going to be off the object, and it's not going to be on that object. And for example, here the centroid might be somewhere here, so it might be the centroid C, and these are the distance we want to find. So uh, again, here we want to find these distances to find the centroid. And as we had before, again, the distances for the centroid here is similar to the 2D. Is going to be this time dl or dl. So the previous one we have the dA, and here we are going to have the dl. So the last time the element, the differential element we had was the area element, and here's the length element. So to do that, first of all, we have to go ahead again last time and choose an element. This time we'll choose the element somewhere along the line. So assume this is the element I'm going to choose along that line, and that element has centroid and the cent and the uh, that centroid uh, for that element has, for example, if I go ahead, it has, this one is the centroid of that, so it's going to be, and this one is also, so it's going to be, so the distance of centroid of that element, and also it has the length of dl. So again, if I look at here, I have to find the location of the centroid of the element. I have to find the location of centroid of element, and sorry, this one is uh, yeah, that's right. So I have to find the location of find the centroid location of for that element, and also how to find the dl. So to see how we will do that, the centroid of that element is always is much easier to find when you have the line. I would say that the x um, the x and y for the element, the centroid of element, it just is equal to x and y. So if you look at that, the 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 y distance of the centroid for the element is y, and the x distance for the centroid of the element is just x. It's much easier just to look at it that way. Uh, uh, Also, now I will go ahead and draw that DL, draw it a little larger here, so we can show what we will do. So if I draw that larger here, and this is going to be DL, then I have these distances here. I'll say this is dx, and this is going to be dy. And I can write that the dl is square root of dx squared plus dy squared. So that's how I can write that. Now I have to write again everything as a function. Depends on as a function of x or as a function of y. I have to decide if I want to do calculation as a function of x or want to do the calculation as a function of y. So if I go ahead, I will say that the first case that I want to do calculation as function of x. So if I want to do the calculation as function of x, this is how we are going to do that. This is what that dl is going to be. I'm going to divide everything by dx squared. So it's going to be dx squared divided by dx squared plus dy squared divided by dx squared, and then times them by dx squared. If I do the calculation again, so I go ahead, this is going to be 1, dx squared divided by dx squared is going to be 1. And here I have dy squared over dx squared, and look at that, it's not the second derivative, it's just the dy to the power of 2 and the dx to the power of 2, so I can just write it as a dy over dx to the power of 2, and then take these out, it's going to be dx. So it's going to be as a function of x. And again, the centroid for the element, I can also find them as that. Now, if I want to do the calculation as all the calculations as a function of y, you can do it the same way. So do calculation as function of y. The same way as we did before, but this time instead of dividing everything by dx squared, we divide everything by dy squared. So I would go ahead and say dl is equal to dx squared divided by dy squared plus dy squared divided by dy squared, and then I times everything by dy squared. And then if I just simplify that, it's going to be dx over dy squared plus 1, and then I take the dy outside, so it's going to be dy. And again, this one, the centroid of that element is going to be x and y. So either we choose this one, we go and write everything as a function of x, and we put in these two equations to find the centroid of that line, or we go with this one, we write everything as a function of y, we replace them in this equation, and we'll find the centroid of line. Okay, let's look at an example. This is a well, 1D rod we have here, and that has the equation y equal to x squared, and we want to find the centroid of that rod if it goes from 0, 0 to 1 and 1. So again, the very first thing we need to do is we have to go ahead and define a small element on that. So we'll go ahead and assume this is the element we choose on that. So this is the element, and then we'll call that element has a length of dl, assume it's the length of dl, and it has a centroid, and the centroid of that element here is located at is equal to x. And then remember, when we are talking about the 1D object, the centroid of the element is equal to x and y. So I have to go ahead and first of all to find the dl, and remember that we have said that dl is going to be dx squared plus dy squared, and then I want to do all the calculation as a function of x, so I would go ahead and then divide everything by dx as I said. So it's going to say dx squared divided by dx squared plus dy squared divided by dx squared, and then I times everything by dx squared. And then I will go ahead and says that, okay, if I simplify that, the dl is going to be 1 plus dy over dx squared dx. And then if I look at here, dy over dx is the y is equal, so it's going to be d over dx of x squared. So it's going to be x squared. So it's going to be 2x. So if I use these two together, then the dl is going to be 1 plus 2x squared, because dy over dx is 2x dx. And then I know that the centroid of element has the dimension of the x and y. So now I know all the information I have. So I have dl, I have the centroid of the element. I can go ahead, but one thing I have to do is that everything I have here is as function of x, so I have also changed this one as a function of x to make sure also this one is a function of a. So I'm gonna replace y with x squared, so I'm gonna have replace the y with x squared, so also this one is going to be as function of x. So everything is now is going to be function of x. So now I can go ahead and say that the centroid for that is going to be integration of the for dl. So first of all, the integration is over the x is between 0 to 1, so it's going to be 0 to 1, and then the centroid of the element in the x direction is just x, and the dl is 1 plus 1 plus 2x squared dx, and then you have, okay, 0 to 1, 1 plus 2x squared dx, so it's a dl. And if we do the calculation for that, it's going to give you 848, and then we have 1478, this is the 0.573. So you can plug either of these integration into your calculator, and then they get the values for that. Almost all the engineer calculator do the numerical integration. The same for the location of centroid. The centroid in the y direction is coordinate plus and again we'll go ahead and it's going to be 0 to 1, because again we are integrating over x because everything is dx, and then the location of the element centroid in the y direction is just x2, so this one is x2, so x squared, and then the dx, then the dl, which is going to be 1 plus 2x squared dx, and then you have the dl. Remember that you have DL here on both of them. So once you calculate the DL, once don't recalculate it again here. We already have the DL. You just can simply use the value you have calculated for the previous step, which is 1.78. So the integration of DL you already have, so you already need to calculate the new one. It's going to be 0.606, which is going to give you 0.410. So if you look at that again, it gives you and again that centroid is not located on the object, is off the object. Okay, let's look at another example. So it's a simple 2D triangle and we want to find the centroid of that triangle. Again, anytime we want to find the centroid, regardless of what object we have to create an element on that object. So it's either for 2D we had the options creating a horizontal or vertical element. So here I'm going to create a vertical element. So assume this is the element I'm going to use in my calculation. So this element is going to have this a dx, and then this distance is going to be y, and then it have a centroid here, and that centroid, if I want that the location of the centroid for this element gonna be x, and then the location the location of centroid the element in the y direction is gonna be half of the y. So I have my element and I have the location of that the centroid, the centroid of that element also. So the centroid of that element. Now I know that when I have the element, there are three things I need to find. After I define my element, I have to define the area of the element and the centroid of that element. So if I go ahead, it says that the area of the element is going to be dA. The area of that element is going to be that y times dx. And because we have dx, it means that everything should be as a function of x. So we have to get rid of that y. And because that we are going to replace the y with this value here. So it's going to be 2 minus x dx. So we have the dx and dA and everything as a function of x. And then we have to write the value of the centroid of the element. So first in the x direction, and we know it's the x, and that's all we need to do. And then for the y direction, we know that is half of the y, and then because we have everything as a dx, we have to get rid of that y and change it to x. So it's going to be also half of the y, and then we replace the y with this value, which is going to be here. It's going to be 2 minus x. So this is going to be so we have the area of the element and we have the centroid of the element. After we find the area of element, the centroid element, we can go ahead and find the centroid of that surface we have. So first we start with the centroid in the x direction. So it's going to be what we have, dA over dA. And if I go ahead and replace those values, so again we are integrating over dx, so we're integrating over x, so it's going to be from 0 to 2, so it goes from 0 to 2, and then the centroid of the element in the x direction is x, and then the dA, we just replace this value here, dx. And then for the dA, the same thing, just replace that value. So it's again, it's a 0, 2 minus dx. And if we do the calculation for this one, the value is going to come out as 2/3. The same thing we can do for the centroid in the y direction. So it's going to be so again, because we are using the dx, we are integrating over the x in the x direction. So it's going to be between 0 to 2. And then this value of the location of the cent the centroid of the element in the y direction, um, which is going to be this value. It's going to be half of, and then the dA, which is all going to be 2. This is the dA, dx, and then we have the dA also 0, 2, and the dA, which is going to be 2 minus x dx. And if you do that calculation, this is what we're going to do. It's going to be 0 over 0, 3 over 3, and it's going to be 1. Again, you can plug in these value into in your calculator, and very simply get the values for those integral. Now let's look at another example. This time I want to find the centroid of this 2D surface. So again, when we want to find any the centroid, the very first thing we need to do is we need to go ahead and define an element. Again, we can define the horizontal element, or we can define the vertical element. So here again, I will go and define the vertical element. It's most of the time much easier to do that in vertical element. So it's going to be this distance going to be dx, and then it has, and this distance is going to be y. And then we have the centroid of that element, and the location of that centroid in the y direction. It's going to be half of the y, and in the x direction it's just going to be x. So before we start to do anything, we need to calculate the element, the area of the element, and the location of the centroid of that element. So we need to find the area and the centroid of the element. So let's start with the area. So the area is dA. The area of that element is dA, and it's going to be y dx. And as you see, because we have dx, we have to write everything as a function of x, so we have to get rid of that y. So we replace it with this equation here. So dA is going to be x to the power of half, and then dx. And then we are going to have to find the location of the centroid of the element. So the centroid of the element in the x direction is going to be just x, and the function of x is okay. And the centroid of element in the y direction is going to be half of the y. So it's going to be half of the y. Just make it mistake here. So it's half of the y. And then because it's the y and everything, we have the dx, we have to write everything as a function of x. So we replace that y with the value from here. So we're going to and replace the y with the x to the power of half. And now that we have them, I can go ahead and start to calculate the x and y, the centroid. So this one is going to be again dA over dA, and we have, again, we are integrating over x, so it's going from 0 to 1, and then this value is x, and dA is again x to the power of half dx, and dA is just 0 to 1 again, x to the power of half dx, and it will comes out as a 0.4 divided by 0.667, or 0.6 eventually. And the same for the y bar, the centroid of the y bar. I'm gonna have dA over dA. So it's gonna be, again, because we are integrating in this x direction, it's gonna be between 0 and 1, and the location of centroid of the element in the y direction is this value, is a half of the power of half, and then we have the dA, which is going to be and then we have the dA here, which if you do the calculation comes at 0.25, and again the same thing, 0.667 should equal 0.375. Remember, we can do the very same thing for that case if we want to do consider the horizontal um, element as well. So if I go ahead and if I draw that here, draw that shape here, and try to see how we can do that with the horizontal element. So if this is the shape we have, it's the same shape there, and then we have the x and y direction. So it's the x, this is the y. I just want to show you how it's going to be the same if I choose the horizontal element as that, and then everything will becomes out the same. So if I go ahead and this time I choose the horizontal element for that, this is going to be my element. So this is going to be the element, and the centroid of the element. This time when we want to find the distance, this is going to be dy, and this distance, if we want to find the distance, if I go ahead, this distance is x, this distance is x, just the x. Therefore this distance, what it is the total one, is 1 minus x, because the total is 1 from here to here is 1. So this distance x is going to be on the x, so this one 1 minus x. And then the location of the so I would go ahead, so remember that this one is 1, just make sure. And so this is 1, also this is 1. So let me draw the line, so make sure it's not gonna so what I'm doing, I just redo the whole thing, just not the whole thing, show that we can do that with the with the horizontal element as well. So also here the centroid of the for that is again the centroid of the element. Now I have to find the centroid of element as well. So if I go ahead again, I need to find the dA, and then the dA is going to be, this time the dA is 1 minus x dy. So it's the area of the element, so it's 1 minus x dy. And because I have dy, I have to replace the x with the y. So the function I have, is the y is equal to x. Therefore, I can say x is equal to y squared. So I can use that and replace the x. So I can go ahead and say it's a y minus y squared dy. So this is the dA. And the location of the element centroid in the x direction. We have, this is the distance I want. I look for that. So it's going to be the x. So it's going to be x and half of this distance. So it's going to be x plus half of this plus half of that distance. And then also again I have to go and replace x because I have the y. I have to go replace x with y. So it's going to be y squared plus 1 minus y squared squared. And then the same for the y squared. We go ahead and look at the location of that y squared is just y. So if you look at that, and then we can replace this equation, these three, dA and the centroid of the element in x bar and y bar equation, and it will gives us the very same answer. So either we choose the vertical element and do the calculation, or either we choose the horizontal element, we do the calculation. They both comes out at the same, The only difference that probably here you can see this one much easier to do the calculation and the integration compared to this one. So you have to choose the one that is much easier to work.